Class, we're going to define functions today. It's a big topic in the world of mathematics. Functions are a big deal. What the heck is a function? A function is a rule which assigns to each x value exactly one, not two, not three, only one, exactly one y value. So a rule which assigns to each x value one and only one, not two, not three, y value. The set of x values has a special name. It's a domain. I don't know what's going on with this. So the set of x values is called the domain. The set of y values is called the range. So with a function, it's some sort of rule. It's assigning to each x value one and only one y value. And I think that's probably enough to jump right into problem number one so I can illustrate what I mean by this rule. Let's see, problem one. Oh, that's sort of small.
I know. Give me a moment. Okay, hold on.
Plus.
There it is.
Yeah.
Oh, yeah,
Now maybe we can see problem one better. No, I really can't see it any better. Plus. There. Okay, that's better. Okay, so here we have this little correspondence table, whatever you want to call it. It says domain, range, and as I'm writing these down.
Oh, that looks better if it is.
Okay, let's see. Look at how it has these arrows. 25, that's the x value, is being assigned to the y value of 7. Is that what it looks like? That arrow's doing there? 11, that's an x value. We know it's an x value because it's labeled domain. Is being assigned 17. And 9 is being assigned 7. Okay. And it asks, is this correspondence a function? Well, let's look at what I've written here. Okay, so 25 is being assigned the y value 7. Remember, domains are x values, range are y values. So it looks like 25, this x value is being assigned only one y value. The number 11, how many y values is it being assigned? Just one. And what about the number 9? What's its y value? 7. Just one of them. Is each one of these x values being assigned only one y value? Yes. Sometimes it's tricky. Students will say, oh, wait, no. The way it's reusing the 7 here, that has nothing to do with it. There's only one arrow coming out of the 9. So is this a function? Yes. It is a function. the natural question to ask, what are you asking yourselves? Probably, well, when would it not be a function? And I'll imagine when it would not be a function. Well, if there were two arrows coming out of any one of these x values, then it would not be a function. Like right here, if there'd been an arrow from the number 9 and it was being paired with 17 also, move what over?
I was just saying use a pencil so we could erase it.
Oh, but I was going to do this and say with this thing right here, if that were there, then your answer would be not a function. Y'all see what I mean by each x value gets only one y value.
So yes, this is a function.
Let's look at number 2. Problem 2. It gives us some ordered pairs, and the way we talk about x value being assigned y value, that sort of lends itself to ordered pairs. So let me write down all these ordered pairs first, and then we'll go through and 4, 10, 22, -8, 34. That x value is being assigned the y value 10. Let's see. 4 is assigned to 7. And 50 is assigned to 7. See, I think this is a 3-part problem. The first thing they want us to do is to write out the domain.
Realize in the instructions they tell you specifically type each answer only once. The domain does not tell you how many times the x value is used. All it says is that it's used. When you look at these ordered pairs, you can tell me what numbers are used as x values. Call it out. I'll type it in. Well, okay, I'll let him. He wants to write it out first, so okay. Go ahead. Tony, you get him started. 4 is used. What other numbers are used as x values? 22 and 50. Notice 4 has already been written down, so you don't write it again. There are all the numbers in the domain. What about in the range?
Let's write that out also. Range. And then we'll type them in. I'll get it started. 10. Now don't repeat any numbers. 10, -8. Still one more. 7.
So, let's see.
Go type those numbers in.
Okay, so that was 4,
22, 34, 50.
50. Notice it's nice of them to already have those set braces for us. And now the range.
10, -8, 7.
And is this relation a function? Yes or no? A relation is just an arbitrary set of ordered pairs. So is that relationship they've given us a function?
I sort of like these little arrows here. Why don't we draw arrows here? And if any x value has 2 arrows, then it's not a function. Like 4 is being assigned the y value 10. 22 is being assigned the y value -8. 34 is being assigned 10. Notice how the 10's being repeated. That's okay.
It's fine to have repeated y values. You cannot have repeated x values in a function.
I was going to let them figure that out in a moment.
Okay, go ahead.
But look at this. 4 and 7. What's just happened? 4 has 2 y values being assigned to it.
So write out not a function.
So let's say not a function, and let's write out why. Even though they don't ask, just say why. Not a function, because 4 has 2 different y values, or 2 y values. So say no. Okay. Well, before we do this one, go back over here and let's summarize what you were saying while I go to you. How, if we look at this function, or this set of ordered pairs, could y'all come up with a way to decide if it's a function just by looking at the y values? Like right here, the fact that there was a repeated repeated x, that means it's not a function. You're going to see 3 ways of defining functions today. First way is like this, as a rule. The second definition, I'll word it like this. A function is a set of ordered pairs with no repeated x values. So if you have a listing of ordered pairs, look right up here. If there's a repeated x,
not a function.
Not a function. Well, what about repeated y's? Like right, look, there's a repeated y, but that's irrelevant, okay? Repeated y means nothing. I'll just say that's okay.
Repeated y.
Those are okay. But there can't be a repeated x if it's going to be a function. Now, we just finished graphing circles, so I have a question for you. Are circles functions? That's the question we're about to ask. Or I'm about to ask, and we're going to answer. Are circles functions?
Draw a circle centered at the origin. That's an easy one to look.
Yeah. Circles functions. To answer the question, are circles functions? I'm going to draw a circle, just a generic circle, if there is such a thing.
If there's such a, I was thinking the same thing. I don't know any circles were just generic terms.
I'm going to draw one, well, pretend it's a circle.
It looks more like an oval to me.
Yeah, well, I'm going to draw a circle centered at the origin with the radius of 2. Each little mark here is 1 unit. So, are circles functions?
Are there any x values that are being repeated? And if so, give me one. There's an obvious x value here that's being repeated.
I'm going to do this right there. Let's write this, assume it's 2. 1, 2. This is a circle centered at 0, 0 with a radius of 2. What's this ordered pair right here?
0, 0.
No.
Is it
0,
2?
2.
Uh-huh. Is there another ordered pair that has 0 as the x value?
0, -2.
Right there. 0, -2. Here are 2 ordered pairs with the same x value. Repeated x. Oops, can't see it. Repeated x, not a function. So, how will I answer my question? Are circles functions? No.
And what you've just developed is something called the vertical line test.
Well,
Even if this y-axis wasn't passing through the middle of a circle, if you can draw a vertical line so that it hits the graph twice, then it's not a circle.
Right.
You draw a right there, passing through 1, hits there, and it hits right there.
These 2 points right here have the same x value. Okay, they're both 1. Like right here, here's two ordered pairs that have -1 as their x value. So
circles are never functions.
in general, this is something called the vertical line test. If a vertical line intersects a graph more than once, the graph is not a function. Do y'all see why I say that?
I always say 2 or more times, but more than once does it, okay?
There are two ordered pairs with the same x value. I can draw this line right here, this vertical line. Here are two ordered pairs with the same x values. Okay?
Look at the next homework problem. This one should be,
Number 3.
there it is.
It's a V. It's asked, basically, I'm not going to draw the graph. What I'm going to write on my sheet of paper is a V a function?
I remember graphing expressions that had these pointed V's. Does anyone remember what the equation would have had in it to get his V-shaped figure?
It
Starts at, here's the hint. Tony's doing a hint. What is that? What has those vertical absolute value? Yes, this is an absolute value expression. Can you draw a vertical line so that it hits this V in 2 spots? I think no matter where you draw it.
See if you pop it out and make it even bigger.
I don't care where you draw it. Are you going to hit the graph twice if it's a vertical line?
Look at all the little vertical lines.
Do any of those vertical lines hit the graph twice?
No.
So this is an example of a function. These things are absolute value functions. So yes.
There's a V. And
Wait, oh wait. Okay, there.
You can draw vertical lines all you want. It's not going to intersect it more than once. So circles are not functions. V-shaped things, absolute value graphs, those are functions.
So yes.
What about problem number 4? I think we've already answered it.
Is this a function?
No.
No, it's a circle. Right there, the y-axis is intersecting it twice. So clearly not a function.
In fact, show my page.
Okay, right. Oh, no, wrong one here. Okay.
This one right here, I'm going to label that problem 4. Right? I mean, it doesn't matter where the circle is or how big or small it is. A circle is not a function, period.
Because you cannot draw a vertical line because you can draw a vertical line that intersects the graph in 2 spots.
Mm-hmm. What about a slanted line?
Oh,
Let's
that's
look
a
at
good
number
question. Look at this slanted line. What do y'all think? Is this a function? Can you draw a vertical line that'll intersect that blue line in 2 spots? It is a function. No matter where you draw that vertical line, you are not going to hit the graph twice. So yes, this is a function.
Mm-hmm. Mm-hmm. I'm going to try to draw something that looks sort of like it.
Oh, wait. Let's see. You got the graph drawn there. Okay.
It's a slanted line of function.
It's a slanted line of function.
The y-axis sure doesn't intersect it more than once. I don't know if you started drawing other. It's not going to, no vertical line's going to intersect it more than once. So as y'all said, what y'all say? Is a slanted line a function? What did you say? Yes? Okay, good. And
Now they want
now
the
there's
domain
more
and
to it.
range. Now they want you to state the domain and range in
interval
notation.
notation. Y'all remember what interval notation is? Those parentheses, brackets, infinities,
Are you gonna-
domain, range.
When we look at this graph, for the domain, ask yourself, does it keep going forever to the left and to the right? What about to the left? Does the graph ever stop? Look at what it's doing. Follow that, trace that blue line. Those arrowheads means it keeps going forever. So I claim starting at 0, every number to the left will be used as an x-coordinate. Even way out here at -1,000,000, I can go up high enough and I'm going to find that graph. So,
Does it go to the left forever and to the right forever?
yes. So the domain is all real numbers.
And the way we'll write that in
Wait a
interval
minute.
notation is parentheses, negative infinity, comma, infinity. If you labeled way over here negative infinity and here positive infinity, it's going to keep going forever to the left and forever to the right. That's what you're saying here. The graph keeps going forever to the left and forever to the right.
Now the range, you're looking at the y-axis. Apply that same sort of logic.
But instead of thinking left, right, what are you going to think?
Up, down. Does this blue line keep going forever to the right?
No, forever up
forever up.
and forever down.
Yeah.
Yes.
Okay. It's going forever up, so that's positive infinity. It keeps going forever down, that's negative infinity. So, using interval notation, you go negative infinity to positive
If
infinity.
someone told you today, say something algebraic, you could say, the domain and range of a slanted line is negative infinity to infinity. Or
And all
real
slanted
numbers.
lines are functions.
Yeah, and all slanted lines are functions. And circles are not functions. Oh, wow, you have a lot of stuff you can say, to impress people.
Say it at the dinner table.
Okay. Yeah, at the dinner table.
Okay, so gotta type the negative infinity,
I asked once
comma, infinity.
we were at a workshop, a Pearson thing, and they asked, could we do something to make it better? And I told them, make a little hot button for that parentheses, negative infinity, comma, infinity, close parentheses, so you don't have to always be typing that in. You have no idea how many times you're going to wind up typing that in this semester. That's the way we say all real numbers. And now y'all know what a real number is. It's anything on the number line. A real number is any number that's not, and fill in the blank. A real number is any number that's not, fill in the blank, it starts with the I. Imaginary.
Okay. What about this graph here? Does it represent a function? No.
Let's see how
Hold on. There. Okay. Right here at the y-axis, it's intersecting that blue curve twice. So I agree with you. This is not a function.
And there's a lot of vertical lines drawn in letters.
You're right. There are a lot of vertical.
Now, here's the tricky thing about domain and range. Is this graph going forever to the left? Is it way over there at negative infinity? Say no. No. What about positive infinity? Is it going to keep going forever to the right? Yes.
Okay, so that means the right side of the domain is going to be a comma, infinity, parenthesis. Okay, hold on. Tony's writing that down.
Well, right now I'm writing that number 6 was not a function, but for the domain, comma, infinity. To the right, it's going forever. It's going to keep moving to the right forever. But it's not going to have that negative infinity on the left. Where does it stop? At what x value? And you got a good eyes to see it. -5.
And is -5 used as a point? I think I'm pointing at it right there, aren't I? It's on the x-axis. -5 is used as an x-coordinate. So, if you're writing your interval notation and you have a -5, what are we going to use in front of the -5? A parenthesis or a bracket? Remember, a parenthesis means the number is not used. A bracket means it is used. So a bracket at -5.
This is some nice graphical analysis we're doing here.
Okay, I'm going to go ahead and type that in for domain. So is everyone clear on why we're using a bracket? -5 is used as an x value. There would have had to be like a little open circle there in order not to use -5, but it's used. So comma, infinity, parenthesis. Oh, parenthesis. No, parenthesis, darn it. Okay, now the range. Now let me blow this up. Okay, does this thing keep going up and up forever and down forever?
I think it looks better. It looks more like it's going up on the small one. I remember one time a student told me when they looked at it the other way, it looked like it was getting ready to turn down. No, don't do that.
It's not turning. The arrow, it's going up, and so it's going to keep going upward slowly. What about going down? Is it going to keep going down forever?
Yes.
Yes, it is. And so, writing the range,
it goes down forever and up forever. Okay, so the range is all real numbers at -infinity, comma, infinity, with parentheses around it. So I'll type that a lot this semester.
-infinity, comma, infinity, right parentheses.
Oh,
okay. Now,
put over here. Oh, and now you're gonna. Okay, we're switching. No real reason. Oh, you turn off my microphone and you turn on yours. Let's see if it'll work.
okay. We're going to have 3 definitions of functions, 3 general definitions. We have the rule, the arbitrary rule function. Definition. We have the ordered pair definition. Now we're going to have the algebraic definition of function. Okay. Algebraic definition of function. A function is an algebraic equation that assigns each number in one set comma, and this one set is called the domain, to exactly one number in another set, each number in one set to exactly one number in another set and this other set is called the range. Okay, so
We formally defined three terms here. Function, domain, and range. Let's see. Let's break this definition apart. A function is an algebraic equation. Well, I know what an equation is. An equation is anything with an equal sign. 1 plus 2 equals 3. That's an equation, but is it an algebraic equation? When did you move from studying math to studying algebra?
That's it,
Arithmetic, I should say. When did you change from arithmetic to algebra? Well, be more specific. What appeared in the equation? Variables. Letters started popping up in the problem. The most common letter that we're going to use to represent domain values is x. Because our ordered pair definition, the function is the set of all x values. But you could use any number. You could use, any letter. You could use a T for time. You could use a Q for quantity. I know we do that a lot in the business calculus courses. You can use an M for, you could use an M for money, what have you. So it can be any letter, but the most common letter is, for a domain value, is the letter X.
Theoretically, you could even use a Y, but why the heck would you do that?
Because the most commonly used variable for a Y to represent range values is Y, because the ordered pair definition of function says that the domain is the set of all Y values. So Y is the most common, but you can use things like P for price, you could use S for height, what have you. You could really use any letter, but as I said, the most commonly used letter to denote range values is the letter Y. And we have something called function notation.
He's going to be ready for that problem number 7 any minute now.
To use function notation, well, first of all, you can't use this notation for anything that's not a function. It's only used for functions, and the equation has to be solved for Y in order for function notation to be used. So solve for the range variable. Then you replace the letter Y with the notation F parentheses X. It's an F with a left parentheses X, right parentheses. This is called function notation, and it's read as F of X. It's not F times X. You say, well, you learned that of means multiplication in previous math classes. Not with this notation. It's read as F of X. Or some people want to be fancy and they say function of X. And just like with variable names, you don't have to use the letter F as the function name. I use C of X for cost functions. I use R of X for revenue functions. I use P of X for profit functions. I use S of T's for position functions in other classes. We'll even see some position functions in here.
Mainly it's F, G, and H are the 3 letters that will be used for functions a lot.
And function notation has a very nice feature. Suppose, here's my function.
So, are we doing number 7 yet?
Okay, let's do number 7 to illustrate it rather than me making up an example. No, that's the wrong one.
Okay.
Find the indicated outputs for the function f of x equals 4x squared minus 3x. Notice for function notation, you can't have 4 times f of x squared or minus 3 f of x. The f of x is acting like a y, and it has to be isolated on one side of the equation.
So this is a formula that will calculate the y value that's being assigned.
So we
So we
want,
have
first of all, f of 0. Let me write that down.
So the number in the parentheses is the x value. It's telling you to calculate the y value. Find the y value that's assigned to an x value of 0.
With function notation, they're asking you, what is the y value when the x value is 0? Rather than having to write out all those words. What is the y value when the x value is 0? They can just say find f of 0. This notation, this special function notation that we're going to be using the rest of the semester, says go to your function, whatever the function is, in this case it's f, and replace every variable you see with 0. So you have 4, replace that x with 0, replace the x with 0, replace that x with 0. Well, this is about to work out very nicely. What's that going to simplify to? When x is 0, the y value is 0. Okay.
0 squared is 0, 0 times 4 is 0, 3 times 0 is 0, you just have 0 minus 0.
So type
So
in
hopefully
0.
the next one will be a more interesting or challenging problem. Let's see. Now, find f of -1. So what you just said right here is the x value, 0, is assigned the y value of 0. What's the y value that's assigned to the x value, -1? That's what it's asking.
So this says go to your function f. Wherever you see a variable, you're going to replace it with -1. So we have a -1 here and a -1 there. This will take a little bit more simplification. Recall your order of operations. You perform the exponentiation before the multiplication. -1 squared. -1 times -1 is equal to 1. So 1 times 4, that's a 4. -3 times -1 gives me a, so 4 plus 3 gives me a y value of 7. So when x is -1, the y value is positive 7.
Do y'all remember that first problem we did today? The domain and range? So right now we have 0, arrow 0. And what's the second one? -1 is assigned what y value? 7. You see?
Okay. Keep going. Did you type that answer in?
No. 7. Oops.
F of 2. So that says go to your function f. Go to your function f, and wherever you see a variable, replace it with, what was it, 2? So
Whatever's in the parentheses, you're going to plug in for x.
So we plug in, replace each x with 2, and then use the order of operations to simplify. What will I do first to simplify this? 2 squared is 4, times 4, that's 16. -3 times 2 will give me a, be careful, a -6. 16 minus 6 gives me a positive 10.
So what's the y value that's assigned to the x value 2? 10.
We could even write it out in We're generating ordered pairs.
Zero,
We have
zero.
the ordered pair 0, 0. We have the ordered pair -1, 7. We have the ordered pair 2, 10. So these functions are generating ordered pairs.
What was that, number 10?
10.
Gosh.
Okay. Number 8, they're going to
So-
give us a new function.
Whatever's in the parentheses, you plug in for x.
Okay, switch over here. Switch over to my paper. Before you write down that number 8, suppose I'm making up one. Suppose there was a fourth option, a fourth part here. Suppose they want us to find f of c. F of c. That says go to your function f. Wherever you see a variable, you're going to replace it with c. It's just a change of variable. We'll have 4 times c squared minus 3 times c. Whatever's in the parentheses, that's what you replace the variables with. If you're lucky, there's only one variable to replace, but here we've had 2. Number 8, now let's go on to number 8.
Oh, look at that, K. They're using the letter K instead of F for function, but okay. So K of X equals X plus 19.
Okay. Now
Find K
Okay.
of 0.
it says, this notation says go. Okay.
It's one of those problems you might be able to do just in your head.
That says, this notation says go to the function k, and wherever you see a variable, replace it with 0 plus 19 is going to give me 19. So we just generated an ordered pair, 0, 19. 0 is assigned to 19 using this new function.
19.
Okay.
Oh, that was a short one. Okay.
Okay. No,
No,
it's
it
not
isn't.
finished.
Okay. How many more do we have? Oh, 5 parts. Okay. So stop talking, Tim.
You're the one talking, Tony. Okay. So k of -8. That says go to my function k. Wherever I see a variable, I'll replace it with.
-8.
So we have -8 plus 19, which gives me a positive 11. So -8 is being assigned to positive 11.
Notice it's getting only one y value. It can never get two y values.
And I know that because this is a function, because they're using function notation. They cannot use that name, comma, x, that k of x or f of x notation. You can't use that if something's not a function. That means for each individual x, there can only be one y value. So k of -11.
Oh.
Says go to the function k, replace any variable you see with -11. So we have -11 plus 19, which gives me a y value of 8.
A lot of parts, but this isn't really difficult. Hey, I wonder if y'all could just tell me the answer on this one.
It says go to your function k, and wherever you see a variable, replace it with 16 plus 19. Is that 35?
Yes.
And I think there's one more. Okay, I'm going to write this one down. K of
B plus 14.
b plus 14. k of b plus 14. We know how function notation works. You go to the function and you replace the variable with whatever's inside the parentheses. So in this case, we're going to replace that one letter x with b plus 14, and we still have that plus 19 there.
I'm afraid your brown looks sort of like your black.
It does, it does. It looks way too much like it.
Should probably use a blue instead of a
We'll see. So we have, well, 14 plus 19 is 33, so I guess that reduces to b plus 33.
Whatever's in the parentheses, you plug it in for the variable. It doesn't matter how strange it looks. Why on earth would you ever want to replace the x with a b plus 14? Well, you do. That's what it told you to do. So, b plus 33. b plus 33.
Any questions? Yes.
How would you write that as an ordered pair? Say b plus 33.
Okay, switch to the paper. Switch to the paper. You have b plus 14 as your x value, b plus 33 as the y value. Whereas something like this one here, that would be a little cleaner. When x is 0, the y value is 19. But whatever's in the parentheses, that's your first coordinate. That's acting like your x value, even if it's a messy thing like b plus 14, that thing right there, that's your y value. Any questions there?
Okay.
I guess I have room down here. I'll try to save paper. Okay, this is number 9. And, oh, I like this. They tell us there are 3 parts to it. They tell us what they all are and what they are right there. So h of x, is that 10x?
10x.
They want us to find 3 things. H of negative 19, H of
10.
and H, well, wait a minute, I'm just going to, let's see, H of negative 19, H of 10, and H of 21.
Oh,
Does it look like a 19, does it? Can y'all tell that's a 19 there? I think that looks even worse. Well, here we go. H of negative 19, that says go to your function h, and wherever you see a variable, replace it with negative 19. 10 times negative 19 gives me a y value of negative. I agree. So when x is negative 19, the y value is negative 190. We'll answer all 3 of these, then we'll type in the answers. H of 10, that says go to your function h, wherever you see a variable, replace it with 10. 10 times 10, that gives us a nice y value of 100. And finally, h of 21, we have 10 times 21. 10 times 21 is 210. Any questions there? Hold on. Oh, that looks better. Okay. So negative 190, 100, and 210.
Negative 190. 100 and 210.
Any questions? Number 10.
Oh.
If you understand this, we can just type the answer in. If you understand what I've said so far. Make it a little bit bigger. What's the answer? What are we going to type in there?
-2n plus 2.
Okay, that says go to your function f, and wherever you see a variable, replace it with n, the letter n like Nancy, so that's negative 2n plus 3. Wait. Any questions there? Okay. I hope the next one's that easy. Yeah.
At least it's just one part.
I know. Yeah.
Question 11. F of x equals negative 3x plus 5.
Negative 3x plus 5.
Find and simplify f of 2a minus 3. Might not have been as easy as the one we just did, but it's not that bad. In words, what am I going to do?
We're going to go to our function f, and wherever you see a variable, replace it with 2a minus 3. So we have the x right there. We're going to have to multiply the negative 3 by 2a minus 3. We still have something stuck on here. What's stuck on? That plus 5. We're replacing the x with the 2a minus 3. What are we going to do to get rid of these parentheses here? Distribute. Negative 3 times 2a gives me a negative 6a. Negative 3 times negative 3 gives me a and a plus 5. That gives me a negative 6a. 9 plus 5 is plus 14. Negative 6a plus 14.
So can you see the ordered pair? 2a minus 3, comma, negative 6a plus 14. Patch that in. Negative 6a plus 14. Negative 6a plus... Oh, wait. How did I get a capital? Is the caps lock on? Yes.
Remember, there's no time you should use capital letters. In my lab, there's no time you should press the space bar. Any questions there? The thing inside the parentheses is the x value. The value of the function is the y value. So let's look at this next one.
Oh.
Remember, we can express functions as ordered pairs. So here, they've given us an ordered pair that's a function. F equals -1, -5, 0, 7, and 7, 5. And they want us to find f of 7. F of 7. Switch over.
The number in the parentheses is the x.
Look at how we make the ordered pairs. The number in the parentheses is the x. The value of the function is the y. So when we look here, that 7 is the x value. When x is 7, what's the y value?
5.
When x is 7, the y value is 5. I agree.
Now, let's pretend that there was another part to this problem. There's only two other problems that you could have on this. You could have f of -1.
Okay. What would f of -1 be? When x is -1, the y value is negative 5.
There's only one more problem that you could have from this. F of 0 equals 7.
Okay. Suppose I'd asked you this. F of 3. Is 3 in the domain? No, 3 is not in the domain. And so we can't determine what's the y value when x is 3 because there's no x value of 3. I'll say undefined.
See, our little rule didn't tell us what f of 3 was. It's not defined. It only gave us f of negative 1, 0, and 7.
The answer they wanted was f of 7.
Oh, let me touch that in.
Type that in. Now, I think there's only one part here.
Yeah.
These little things here are just things we made up. There's the answer. So we can look at graphs as functions as equations. We can look at functions as ordered pairs. There's another way we look at functions graphically. So let's look at number 13. Okay, number 13. Well, at least they give us I think, I'm not sure. I think we'll write down the four parts.
A, B, C, D.
F of
I'm going to blow up the
4,
graph.
F of 0, F of 1, and F of 8.
The number in the parentheses is what? The x or y?
The x. So looking at that first one, when x is negative 4, x is negative 4, you have to look at the graph and determine the y value. Look at that graph. When x is negative 4, what's the y value? 0. I agree.
Let's see what he just wrote.
When x is negative 4, looking at the graph, the y value is 0. What about f of 0? What would f of 0 be? When x is 0, what's the y value? Look at the graph. Okay, I agree. When x is 0, the y value is 8.
Now write those as ordered pairs.
Okay, so we're seeing the ordered pair. Negative 4, 0. This thing, we had the ordered pair 0, 8.
Now, start here. Complete the y value. Oh, what's the y value of the point? That's what it's asking. Fill in this ordered pair. When x is 1, look at the graph and see the y value. Let me see. When x is 1...
Count up. Where is that? Is that 6?
Oh, can y'all? Do I need to make it bigger? I should have made it a little.
There, I think I can see it better now. But you gotta shrink it down. Yeah. But x is 1. The y value is 6.
It 6?
So we just now created an ordered pair. When x is 1, the y value is 6. What about f of 8? When x is 8, what's the y value?
Here.
It's also 8, isn't it?
Goes all the way up top. Remember years ago, a class that went horribly wrong, okay? Where we wound up spending like 30 minutes on this one problem, and this was before they were combined. I think Tim would have stopped it before it got so bad. But the students, there was a few vocal. They wanted to do the problem. How would they do it without the graph? How do they get the answer if they don't want to look at the graph? And I was like, oh.
In this case, you have to look at the graph.
You've got to look at the graph.
But we know how to handle it. If they gave us a set of ordered pairs, it'd be like number 12. If they gave us an equation, it'd be like numbers 7 through 11.
And I tried to
type
say
in the
that,
answer.
but
Not very well. I think your communication skills were sort of poor that day.
Yeah, they were. I wasn't
And
expecting.
realize you're not typing in the ordered pair, you're just typing in the Y value. And 8. Make it a little bit bigger. Any questions? So we know how function notation works, correct? And when we come back to this one here, this number 12, the way we looked at, okay, 3 isn't in the domain, and we can easily tell 3 isn't in the domain because all the ordered pairs are listed, and there's no ordered pair that has an x value of 3. But suppose we're looking at an equation. What numbers could we plug in for x? Could we plug in 50? Could we plug in the 50 here, square the 50 and put a 50 there? Could we plug in a 50? Could we plug in 1/2?
Yeah, it might be a little messy,
It'd be
but
messy,
you could do
but
it.
you can. So here's the how we're going to determine the domain of algebraic functions. To me, an algebraic function is one that's written as an equation with variables.
But wait, I want to show them real fast.
What we're about to start.
Yes. Find the domain. If it's given to you like this, like a formula, how do you know what the domain is?
What numbers can you plug in for x?
Well,
okay.
Nice little rules.
Let's see. I'll say unless told otherwise. And in other classes like my business calculus class, we're told otherwise. There are plenty of times they say, here's a cost function and assume that it only works for x values greater than or equal to 100. So sometimes they just tell you out, specifically tell you the domain, especially if it's in an applications course like that business calculus class of mine. But otherwise, unless you're told otherwise, assume the domain of an algebraic function is the set of all real numbers comma that when substituted for x is the set of all real numbers that when substituted for x produces a real y value. Well, there have been 2 times that we were working with algebraically, and we ran into things that were not real numbers. There are 2 instances I can think of. One of them involves square roots. If you have the square root of a negative, then that result isn't a real value. So here are the things you want to avoid. There are 2 general topics you want to avoid. You want to avoid the square root of a negative. Now, in order to pick up the square root of a negative, your function has to contain a square root symbol. When I look at numbers 7 and 8, there's no square root there, so we don't have to worry. You can sit here plugging in numbers till the end of time, and you're never going to get an imaginary y value because there's no square root. If there's no square root in the function, you can't get a negative under the square root. So you want to avoid the square root of a negative number. There's another time that we've been working and we got undefined results. This was during the 2nd week of the semester. When else could we get undefined results?
And a number goes to 0.
Okay, there it is. The other, you want to avoid the square root of a negative. You want to avoid denominators of 0. Those are the biggies that cause problems.
I'm going to go back to this number 7. When I look here, the first thing I see is there's no square root. There's no square root appearing, so there's no way I'm going to get the square root of a negative number. So I don't have to worry about imaginary y values. What about denominators of 0? Are there things that I can plug in here that are going to give me a denominator of 0? In order to have a denominator of 0, what do you have to have appearing in the problem? It reminds me of those denominator cut points. In order to have denominator cut points, what did your inequality have to have? A fraction. In particular, you got to have a denominator. When I look here at number 7, I see no fractions, no square roots. Unless they tell me otherwise, I assume the domain is all real numbers, negative infinity to infinity. No fractions, no square roots in your function. Unless they tell you to assume otherwise, you assume the domain is all real numbers. And we'll start off here with number 15. Find the domain of the function. Find the domain. Will this function produce imaginary numbers? Do you see any square roots? Yes, you see square roots. I see squares, but I don't see a square root symbol. Let me write this down. This is number 15. F of x is equal to x squared minus 9x plus 12. What's the domain? Do you see any square roots that could produce imaginary numbers?
-9. -9.
No, -9 is 81. No, -9 times -9 is another 81. So we have 81 plus 81 plus 12. Okay, so I'm doing a bad job of saying this. Okay, let's look at something different. Hold on. Okay, I'm going to come back over here. Suppose I wanted to look at number 17. Where's number 17? I'm doing a bad job at saying this, Tony, but don't. When I look at this function, there's something appearing there. What's appearing there? We haven't seen one of these things today, I don't think. That square root. That's when you got to worry about imaginary numbers. In order for a function to produce imaginary numbers, you have to have a square root appearing. So let's go back to that problem we were just doing. What was it, number 15? I'm going to ask the question again. Could this function produce imaginary numbers? In order to produce imaginary numbers, what would we need to see? A radical. Do we see one? No. So it's not going to produce imaginary numbers. What about undefined results? Denominators of 0. Will you get a denominator of 0 at any time? No, because there's no what? No fractions appearing. No fractions, no square roots, unless they tell you otherwise. What you assume the domain is? All real numbers. Negative infinity to positive infinity. I'm going to write that out. No square roots, no fractions. So unless they tell you otherwise, assume the domain is all real numbers. And I'm going to make up one now. Let's see. F of x equals, suppose instead of an x squared, that had been an x to the 5th minus 9x plus 12. What's the domain?
parenthesis, negative infinity, comma, infinity.
No fractions, no square roots. All polynomial functions have domain, all real numbers.
I think, had you already done this one? Oh, yeah.
Mm-hmm.
Okay.
I remember years ago having lunch with Dr. Sheen, and well, first of all, his classroom used to be right by a door to the MC building that I would come and go through, and I remember walking past his classroom, and I heard him say to his class, "No fractions, no square roots. The domain's all real numbers." And I remember I was teaching functions that same day. This was in 1991, by the way. And
Way before y'all were born.
I thought, that's a good way of saying it. Okay. And I remember, and I always say that to my class. It was a few years later, and we had lunch with Dr. Sheen. Used to be twice a year. Now we've cut it down just to once a year. And I remember sitting there at the restaurant with Dr. Sheen, you know, someone, a casual acquaintance. What do you really talk about? You want to talk about anything real personal? I remember saying, "Oh, wow, I was teaching functions today, and I said it the way you said it. No fractions, no square roots, the domain's all real numbers." And Dr. Sheen was like, "What?" And he literally got his napkin and wrote it down. He said, "Oh, that's a good way to say it." And it was some flippant remark he made one time in class, apparently. He never said it again. And when he heard me say what he had said, he said, "Oh, that's a good way of saying it." He'd say it like that. I'm like, "Wait a minute, I got it from you." But anyway, let's go back to number 14. I'm beginning to, I was just thinking, I was going fast. I was, trying to get through this quickly. And then I
slowing down.
Well, here's number 7.
Number 14.
Number 14. F of x equals 7 over x minus 3. And we want to know the domain. Switch over to the first thing I ask myself, will this function produce imaginary numbers? In order to produce imaginary numbers, you have to see what? A radical? Well, will it produce, there's no radical, so we don't have to worry about imaginary numbers. What about undefined results? I see a fraction. Think about how you determine those denominator cut points. You don't want the denominator to be what? So you don't want that denominator to be 0. That means x cannot equal 3.
Well, what can it equal?
It can equal anything other than 3. You can plug in 50 million for x if you wanted to. You can plug in pi for x. The only number you can't use is 3. I prefer to write out the domain in words. All real numbers.
And this is how it used to be done.
Except 3.
Back in the olden days. You wrote it in words. I remember a graduate advisor saying, write it in words so that someone that doesn't know math can still read it as long as they can read the English. You know, my sister, who I'm sure she's forgotten every bit of algebra she ever learned, could read the phrase all real numbers except except 3. Okay.
But interval notation, I'm sure my sister would have no idea what that is. Y'all need to help me now. We need to write this. My lab requires interval notation. How do you say this without writing it out in words? There's 3. You don't want to include 3. Remember with the denominator cut points on the cut point method, how did you always label denominator cut points? Open or closed?
Open.
Open. You don't want to shade there. But you can use anything else. It's shaded everywhere else.
Every number except 3.
We can't say negative infinity to positive infinity because that would include 3. So we're going to have to make this 2 separate intervals. Notice it's not a closed circle. It's not a bracket. It's not a closed circle at 3, so we're not going to have a bracket. So we have parenthesis, negative infinity, comma 3, parenthesis, or you tell me how we say the second one. Call it out as if you were typing it in.
infinity.
Okay.
See, that is the way we now say all real numbers except 3. And I don't really think that that's good for mathematics. It makes it more,
Obscure.
yeah.
It makes it more
It's more
obscure.
intimidating because at least my sister could read that, all real numbers except 3. But if I brought her in here and told her to read
To
this,
interpret that,
she'd have no idea. And that's one of the problems with why, math class is hard. Like right here, answer A would be all real numbers except what?
0.
What about D?
3 and 0.
Yeah,
That's
all
right.
real numbers except 3 and 0. But wait, which one did we want?
C.
C. So, it's unfortunate that math is nowadays.
Math class is hard.
Yeah, it is.
Y'all
Because we
remember
have
that
all this.
scandal back in the 90s? Y'all weren't born yet. They had a Barbie doll.
And
and
she'd say math class is
She had
hard.
these little phrases, and one of the phrases she said was, math class is hard. And I remember seeing the commercial thinking, now why are they
Why are
doing
they
that?
doing that? Little girls are now saying math class is hard when little girls are doing just as good as little boys in my class,
I remember that, and I remember the scandal. I mean, we weren't the only ones that were upset by it. Mattel or
You
whoever.
eventually had to stop it and change it to what?
So
I think they
did-
changed it to math class is fun or something like that. Oh, okay, that's good. Math class is hard. That's not a good. I claim there's 2 numbers you can't plug in for x. Like on the second fraction, you can't plug a 5 in because that'd give you 9 over 0.
What number could you not plug into the first fraction?
What would give us 0 down here?
-5. Switch over. It doesn't matter. Okay,
You're gonna
so
write
I'm
it
gonna
all
write
out.
it out anyway. First question I always ask myself, will the function produce imaginary numbers? And the answer is, to produce imaginary numbers, you have to have what symbol appearing? A radical. There's no square root, so we don't have to worry about imaginary numbers. Will it produce undefined results? Yeah, there are 2 fractions. We don't want either of those denominators to be 0. So x can't equal here. -5, I agree. Here. So, oops, not equal. Not equal. So, can x equal 50 million? Yes. Could x equal 7? Yes. What are the only numbers that you cannot plug in for x to create a y value? -5 and +5. So if we were going to write it out in words, the way I like to do it, all real numbers except -5 or +5.
And of course, it can't be like that. You got to write it in interval notation. So picture a number line in your head or draw the number line.
I'll draw the number line. I'll do better than picture it, Tony. There and there. And remember, this is, to the left is what? Negative infinity, and to the right is positive infinity. You can use any of these numbers. You can use any of these numbers and any of those numbers.
Everything except -5 and +5.
So, will our interval notation have any brackets in it?
No.
No, because there's no closed circles. So the first interval, parenthesis, negative infinity, comma, -5, right parenthesis, union. How do we say that middle interval? This middle interval is everything between -5 and +5. Not including -5 and +5, just the stuff in the middle.
You said parentheses -5, comma 5.
Mm-hmm.
Union. This last interval, parenthesis 5, comma, infinity.
This is a multiple choice.
Oh, it is a
I
multiple
don't know. I
choice.
mean,
Yes, it is.
So all of that to mean every number on the number line except -5 and 5. Let's see. So A is for every number except -5 and 5. B is just every number except 0.
What's C saying?
You say all real numbers.
All
Yeah.
real numbers. What's D saying? Every number except for just -5. I think, well, the only one that has 3 intervals has to be A. Okay, I want you to look at 17 and 18.
Okay.
Look at 17. 17 has that, let me write it down.
17 has a square root symbol, and I'm thinking that's probably what stands out to y'all.
And
18.
18. Let's see. F of x is equal to 1 over the square root of x minus 15. Okay.
Okay, 17 and 18. What's the difference between the two of them? They both have square roots.
But what's the fundamental difference between 17 and 18 and all the other ones we've already done?
Is it a fraction point?
What I'm looking at is that square root. The
Oh, yeah.
square root is the thing that makes these different from the others. Now, look
But
at where
the thing that distinguishes, separates them apart is that 18 has a fraction and 17 doesn't.
I think it might be easier for you to follow my logic if, let's look at 18 for a moment.
You're going to do 18 first?
No, we're just going to talk about it. And then we're going to write up a little guideline, okay? When I look here, I see the square root.
Wait, let me show what
I'm not working this out yet. I just want to have something to point at so I can make a little guideline for us, a little recipe, if you will. When I look here, I know I can't plug in something like a 1 or 0. If I plugged in 0 for x, 0 minus 15, I'd have the square root of what? Negative 15 in the bottom? That's imaginary. So it can't be all real numbers. Well, remember, can you allow the denominator? So we can't let this thing down here be negative. If you plug in something like 3 minus 15, that's the square root of negative 12. That's imaginary. You can't have an imaginary y value because you can't label an imaginary number on a y-axis. But it's a denominator, so we know the denominator can't be 0. This thing under the radical, it has to be greater than 0. It can't equal 0. If you plugged in 15 here, 15 minus 15, what have you just gotten for the radical? I mean, for the denominator? 0. So I'm looking at two cases. The first case and the second case. This is for domains of square roots. I'm looking at the second case first. If the square root is in denominator, if the square root is in the denominator, then the thing that's under the square root, the thing under the square root, recall the thing under the square root is called a radicand. I've used that term before. That's the thing under the square root. Usually I just call it the thing under the square root, but here I think it's better to use the formal terminology. If the square root is in the denominator, you set the radicand just greater than 0 and use the cut point method.
It's going to seem very strange because you've never done a cut point problem this easy. Okay? But why are you just saying greater than? Why not greater than or equal?
Because if you set it equal to 0, then you're going to wind up with a 1 over 0 here, and we know a denominator of 0 is undefined. So if the square root's in the denominator and you're trying to find the domain, just set the radicand greater than 0.
Use cut points.
and use cut points.
Now on number 17,
Can you get a denominator of 0 here?
is it okay to have a 0 under a square root?
It's the square root of 0. Is that a real number? What's the square root of 0 equal? Just 0. So if the square root is not in the denominator, then it's okay for the radicand to equal 0. So if the square root is not in denominator, you set the radicand greater than or equal to 0 and use cut points.
It's going to seem strange just because you never had a cut point problem
That
this
easy.
easy to solve. It's not hard. But looking at this, on a calculator, the square root of 0, if you punch that in, it says 0. But if I go 1 divided by the square root of 0, look at the error warning it's going to say. Error, divide by 0. It's okay to have a 0 under a square root, but you can't have it in the bottom of the fraction. Okay?
So let's just do, well, I'm already looking at number 18, so let's do 18 first. I look there, I see that there's a square root, so I know this is going to make imaginary y values. We have to discard numbers like 0 and 1 and 2, because if you plug those in, you get negative numbers under the square root. So we set the radicand. What's the radicand?
Right, and it's negative 15.
Well, it's just x minus 15. The entire thing that's under the radical is called the radicand.
Oh, wait.
So,
Calculator, let me
Set
move
x
that.
minus 15 greater than 0. You don't want it to equal 0, because then you get a denominator of 0. And so using cut points, x minus 15 equals 0. That means x equals 15. That's my solution cut point. And notice, once I set up the inequality, I'm not looking back at the original problem. Here's my inequality that I'm solving. I find my solution cut point. I draw my number line. There's 15.
Open or close?
Open or closed? Look at the inequality we used. Will it be open or will it be closed? Open. Now, one side of 15 produces real numbers. That's the side we want. The other side produces imaginary numbers. That's the side we want to cross out. Which side is acceptable? Which side produces the real numbers? Well, let's test a number. What number do you want to test?
0.
0. Which interval contains 0? The interval on the left or the interval on the right? The left, we're going to test 0. That'll give me a 0 minus 15 is greater than 0. Negative 15 is greater than 0. True or false? False. So we cross out that side. That means this side over here. If we plugged in 16 to test, suppose we had plugged in 16 to test. 16 minus 15, that's a positive 1. That's a positive number. It's this side to the right that's acceptable. Any questions on my logic there? So how do we say this shaded interval using interval notation? They're going to want the domain at interval notation. How are we going to say that? The left-hand endpoint is a 15. Do I have a parenthesis or a bracket? I couldn't hear you.
The denominator and cut point is the parentheses.
Well, it's a parentheses, 15, comma, infinity.
So any number bigger than 15.
So that's saying you can plug in any number that's bigger than 15 for x, and it'll give you back a y value that you can label on an XY grid.
And you can plug it into your calculator without getting an error.
Right.
So this is number 18. And is it multiple choice? Let's see.
It is.
Yeah. Oh, wow. Look at B and D. They're tricky. Which one am I going to use? D. You see, this says including 15.
If you plugged in that 15, you'd get 1 over 0.
If I went 1 divided by the square root of 15 minus 15, it's about to give an error warning.
Divide
Why?
by 0.
You're dividing by 0. So we can't plug 15 in. Sometimes students say, well, why not just say 16? Yeah, you can plug 16 in, but there's a whole lot of 15 point that you can also plug in.
Infinitely many.
Yeah.
The real number system is dense between any two real numbers.
Okay.
Is infinitely many more real numbers. There are infinitely many numbers between 15 and 16. 15.1, 15.01, 15.001, 15.0001. You can
Okay.
just keep on sticking in that
Are
zero.
we ready to do number 17?
I think we are.
Yes.
And on our notes, we labeled it as an SCP, but would it not be labeled as a GCP?
Well,
Well, you see, that's why I said just ignore. Just ignore. Once you set up the inequality, just ignore the
but if you want to
original
think
part.
of it, oh, that's a domain cut point.
Then that
Open,
answers,
yeah.
that's explaining. But I've already said it's going to be an open circle, so.
But you're right.
But you're right about that.
Uh-huh.
Mhm.
So whether you call it solution cut point or denominator cut point,
I called it a solution cut point with an open circle, but it's really a denominator cut
Wait, I
point.
messed up.
But I'm just trying to make it as similar to the others. When there's a square root and a not in the denominator as possible. If the square root's in the denominator, you set the thing under the radical greater than 0.
So it's easier to compare.
I couldn't hear you.
Put it as an SCP, so it's easier to compare.
Yes. This one here, okay, once again, we can't, it's going to generate imaginary numbers. If we plug in something like, say you plug in something like
10.
10.
20 minus 50, that's going to be negative under the square root.
So you can't allow it, but it can equal 0. The square root of 0 is 0. It's 1 over the square root of 0. That's undefined. That's the problem right there. But it's fine to equal 0. So that's what I said, but there's no recipe here. If the square root is not in the denominator, you set the radicand greater than or equal to 0.
And
So-
wait, Tim, go ahead and use closed circle here.
Okay, this one here, use closed circle. That's a good idea.
Whereas if I were going to do something
Down
similar
here-
down here, if there's a denominator,
Use open circle. There versus there.
trying to distinguish between these two different types of square root functions.
So this is not in a fraction. We know we need 20 minus 5x to be greater than or equal to 0. So using cut points, we set 20 minus 5x equal to 0. That says negative 5x is equal to negative 20. Divide both sides by negative 5 to give me x equals 4. So there's the cut point. 4 is going to appear in the domain. And since equality is acceptable, close circle. Which side do we want to cross out? A moment ago you said what? Use 10? You were testing 10, Tony? Suppose we tried to test 10.
But if I were just doing it, I'd test 0.
Yeah, you're right. I'd test 0. So which interval contains 0? Left or right? Left, I agree. So we're going to test 0. 20 minus 5 times 0 is greater than or equal to 0. That says 5 times 0 is 0. Is that a true statement? Is 20 bigger than 0?
Yes.
Yes. So here's the side you shaded. If we had tested 10 the way Tony said a moment ago, if we had tested 10, do you agree 10 would be out here to the right of 4? So you test 10,
And you
that
don't
would
have
be
to. You already
20
got the answer.
minus 5 times 10 is 50. Is that bigger than 0? No, it isn't. When you knew this side checked, you knew that side didn't. How do we express that using interval notation? Call it out as if you were typing it in. Parentheses, let's see, parentheses, negative infinity, comma, 4, what's going to go after the 4? A bracket. Good. I'll write it here. Negative infinity to 4 bracket. That's saying the numbers you can plug in for x are all the numbers to the left of 4, including 4.
Can you plug in 5?
Can we plug in 5 there and get a y value? No.
Can we plug 1,000 in?
No.
Can we plug a negative 1 million in?
Yes, because it's to the left of 4.
Let me type that in. Oh, wow. We're going to be through. Oh, wait. Oh,
No, go back.
okay. Oh, here we got to type it in. So parentheses, negative, infinity, comma,
4,
4,
bracket.
bracket. Oh, check it. Okay. So
I think there's another
yeah,
problem.
there is. But y'all see the difference between 17 and 18.
18.
Okay.
And hopefully you see the difference between 19. Let's look at 19.
Are we going to have to use cut point on number 19?
Well, show us 19. Let's see. Oh, there it is.
We're going to have to use cut point. Say no.
No, because what's not appearing in the function?
Yeah.
There's no radical.
Those square roots. That's when you got to do that. Draw the number line and test the interval.
And it says, find the domain. Do not use a graphing calculator. Well, I don't know.
If you want to use a
the
graphing
calculator and you know how to do it, do it. But what I do, first thing I do, I ask myself, will this produce imaginary numbers, square roots and negatives? And the answer is no, because there's no radical. Will it produce undefined results, denominators of 0? And that answer is yes. We don't want that denominator to equal 0. So x squared minus 2x minus 8 cannot equal 0.
You're doing number 19 the same way you did. What was that great problem?
There it is, number
here.
16.
Number 16.
Here, well, you don't have to factor the denominators, but here, this thing's factorable.
Once you factor it, it's going to be just like that problem we just showed.
Mm-hmm. So x squared, what will I use?
X.
X times x. It's a simple trinomial. Okay, the last sign's a minus, so what do we know about the signs? Okay, so we're going to have a plus and a minus. Now for 8, either 1 times 8 or 2 times 4. Remember, you choose the pair that subtracts to give you that minus 2x there. We said there'd be a plus and a minus. Play it out in your head. Plus 4 and a minus 2. I think that's reversed. I think that's going to be a positive 2x, isn't it? And so I think it's going to need to be a negative 4 and a plus 2. Let me mark that out. If you all agree, that gives me the outer product is a positive 2x. What's the inner product? 2x minus 4x gives me a negative 2x. Is that what I needed? Yes, it is.
And so this is where Tony's saying that it's like number 16. You have two different factors. Neither of them can be 0, so x minus 4 can't be 0. X plus 2 cannot be 0. So x cannot equal 4. X cannot equal negative 2. And how do we say that using interval notation? We don't want those shaded. How do we express that using interval notation?
All numbers except.
If I were writing it out in words the way I like to do, all real numbers except for negative 2 and positive 4. But they're not going to let me write it out in words. I got to use interval notation. So call this one out to me. Parentheses, negative infinity. Common negative 2. What goes after the negative 2? Parentheses. I may as well ask right now, will we have any rectangular brackets? No, because there's no closed circles. Or the numbers between negative 2 and positive 4. How do we denote that using interval notation?
Negative 2, comma 4.
Parentheses. Or okay, there it is.
All of
And I think
that
this one we're going to have to type all
the
that
same.
in.
All numbers except
Negative 2 and positive 4.
Okay, so let's start typing. Parentheses. Negative infinity,
comma, negative 2,
close parentheses,
union,
parentheses, negative 2, comma 4, close parentheses, union, parentheses, 4, comma, infinity. Now really, when you think about, as I'm typing this, what I'm typing is all numbers except negative 2 and 4. I can understand students throwing their hands up in the air saying, wow, well, why can't we just say all numbers except negative 2 and 4? Well, that's not up to me to decide. Someone else decided it, Pearson.
And from a programmer's point of view, it's a lot easier.
Oh, look, we got 100 on it. Okay.
Oh, fancy that.
Yes, you got them all right.
Any questions? Okay, stop recording and remember.